Perlin noise is something I found fascinating ever since I started programming. I used the noise in some of my past projects, like my Terraria clone. However, it was through the use of a library. So that's what we're doing today, going over a few different types of noise, explaining how they work, and showcasing code to see how I implemented them. To start off our little journey, I'll first add the simplest kind of noise, white noise. I very simply applied a random function to each pixel of a square which fills the entire screen, which results in a static looking mess. Perlin noise, founded by this elegant chap, uses some interesting techniques. Before we do anything, we first need to initialize our permutation table and gradient table. These two tables are essential for generating pseudo-random values used by the Perlin noise. The permutation table determines which gradients are selected at each point, while the gradients and the interpolation functions are what allow the final noise to appear smooth. First, we set the size of both of the arrays to 256 plus 256 plus 2, giving us a total of 514 elements. This extra space will become useful later when we access the tables using wrapped or repeated indices. We then populate the first 256 elements of both arrays. The permutation table is initially filled with the values from 0 to 255 in order. The gradient table, meanwhile, is filled with gradient vectors. These vectors represent directions that will later be used to calculate the noise value at each point. Next, we shuffle the permutation table to introduce pseudo-randomness. The algorithm used for this is known as the Fisher-Yates shuffle, also commonly called the Knuth shuffle. The shuffle works by looping through the valid size of the array. In this instance, there are 256 elements, thus we loop as long as I is lesser than b. K is assigned the element in the index I of the permutation array. Then, index j is set to a random value between 0 and 256, which we set our element to. Finally, we set the permutation table element at index j to the initial value stored in k. This way we switch them around and there's no repetition in the array. Finally, you may have noticed that we have only populated the first 256 elements of our 514 element tables. The final loop fills the remaining elements by repeating the values from the beginning of the tables. In other words, the second half is a copy of the first half. This duplication allows us to access permutation and gradient values beyond index 255 without having to constantly perform a modulo operation. Let's look at a single fragment during the execution of the Perlin noise algorithm. Imagine that our fragment is located somewhere inside a cell, or a square. We can label each corner of the square so that we can refer back to them later. First, we calculate the offset variables that describe the fragment's position relative to each side of the cell, later used to calculate the vector offsets from the corner of the fragment. These offsets tell us how far the fragment is from each wall and will be used when calculating the dot products. Next, we use the fragment's coordinates, together with our permutation table, to generate pseudo-random indices. These indices are used to select a unique gradient vector for each corner of the cell from our gradient table. We then calculate the dot product between each corner's gradient vector and its corresponding offset vector. This gives us a value for each corner that represents how closely the gradient direction aligns with the direction from that corner to our fragment. Finally, we interpolate between these corner values using smooth fade function. Rather than simply using linear interpolation, Perlin noise uses a specially designed curve that gradually changes the interpolation weight, producing a much smoother result. The result is a single noise value for our fragment. The value can then be mapped to a color, allowing us to visualize the Perlin noise pattern across the entire image. Brownian motion is dependent on Perlin noise, as it essentially layers a bunch of different noise maps on top of each other and merges them using frequency and amplitude parameters. An octave is just a single layer of noise, so by looping through 4 octaves we generate 4 different noise maps, with increasing or decreasing frequency and or amplitude values, and merge them together. Using Dear IMGUI, this library, we can view in real time how frequency, amplitude, and the number of octaves affect the output of a noise map. Also, you might spot these two other parameters down here, gain, and lacunari. I can't read today. Both of these are used to scale the amplitude and frequency with each octave. These types of noise maps, but not exclusively, are popularly used when procedurally generating textures, clouds, terrain, and more, which I can't really think of from the top of my head. Last but certainly not least is cellular noise. It's called that for its striking similarity to biological cells. Notice how each cell differs with size and shape. We achieve this result through a simple process. First, we divide our texture space into a grid. This helps with the performance. Then we loop through the 9 tiles around the current fragment, finding the smallest distance between the fragment and the pseudo-randomly selected points around it. This distance is then used to color the fragment. Cellular noise can be used to procedurally generate textures too. Think of water shaders, realistic cell-like textures, perhaps cobblestone-like textures, or reptilian scales, or more. Anyhow, I'll skedaddle off and start using these noise maps in practice. I'll come back somewhen in the future to showcase my creations. Till then, see ya!